Okay, so here the coefficient next to A1 is, well, we delete this column and this row, and we are left with B2, B3, C2, C3. Next, the next one, we take A2, we delete the row that's in it and the column that it's in, and we are left with B1, B3, C1, C3. And similarly with A3, we take what remains, that's B1, B2, C1, C2. Finally, last but not least, there's a minus sign here for the second guy. Okay? So, well, it looks like a weird formula. And I mean, it is a little bit weird, but it's a formula that you should learn because it's really, really useful for a lot of things. So I should say, if this looks very artificial to you and you'd like to know more, there's more in the notes. So read the notes. They will tell you a bit more about what this means, where it comes from, and so on. If you want to know a lot more, then someday you should take 1806, linear algebra, where you will learn a lot more about determinants in n-dimensional space with n vectors. And there's a generalization of this in arbitrary dimensions. In this class, we'll only deal with 2 or 3 dimensions. Yes? Sorry, why is the negative there? Well, that's a very good question. It has to be there so that this will actually equal, well, what I'm going to say right now is that this will give us the volume of the box with sides A, B, C. And the formula just doesn't work if you don't put the negative. There's a more fundamental reason which has to do with orientation of space and the fact that if you switch 2 coordinates in space, then basically you change what's called the handedness of the coordinates. If you look at your right hand and your left hand, they are not actually the same. They are mirror images. And if you swap 2 coordinate axes, that's what you get. That's the fundamental reason for the minus. But again, I mean, we don't need to think too much about that. All we need in this class is the formula. So why do we care about this formula? It's because of a theorem that says that geometrically, the determinant of the 3 vectors A, B, C is, again, plus or minus. This determinant could be positive or negative. See, there's minuses and there's all sorts of stuff. Plus or minus the volume of the parallelepiped. That's just a fancy name for a box with parallelogram sides, in case you wonder. With sides A, B, and C. Okay, so you take your 3 vectors A, B, and C, and you form a box whose sides are all parallelograms. And then its volume is going to be the determinant. Okay. Other questions? Oh, at the back. I'm sorry, I can't quite hear you. Yes, we are going to see how to do it geometrically without a determinant, but then you'll see that you actually need a determinant to compute it, no matter what. So we are going to go back to this and see another formula for volume, but you'll see that really I'm cheating. I mean, the important way, I mean, somehow computationally, the only way to compute it is really to use a determinant. Yes? That's correct. In general, I mean, actually, I should say, if you look at the 2-by-2 determinant, see, you can also explain it in terms of this expansion. You take A1 and multiply by this 1-by-1 determinant, B2. Then you take A2, you multiply it by this 1-by-1 determinant, B1, but you put a minus sign. And in general, indeed, when you expand, you would start putting plus, minus, alternatingly. More about that in 1806. Yes? There's a way to do it based on other rows as well, but then you have to be very careful with the sign factors. So I'll refer you to the notes for that. Okay, if you did it with, you could also do it with a column, by the way. Just, be careful about the sign rules. So given how little we'll use determinants in this class, we'll use them in a way that's fundamental, but we won't compute much. So let's say this is going to be enough for us for now. Okay, so after determinants, now I can tell you about cross product. And cross product is going to be the answer to your question about area. Okay, so let me move on to cross product. So cross product is something that you can apply to two vectors in space. And by that I mean really in three-dimensional space, okay? This is something that's specific to three dimensions. So the definition, A cross B, so it's important to really do your multiplication symbol well so that you don't mistake it with a dot product. Well, that's going to be a vector okay, so that's another reason not to confuse it with dot product. Dot product gives you a number, cross product gives you a vector. So they're really completely different operations. They're both called product because, well, somehow one couldn't come up with a better name, but they're completely different operations. Okay, so what do we do to do the cross product of A and B? Well, we do something very strange. Just after I've told you that a determinant is something where we put numbers and we get a number, I'm going to violate my own rule. I'm going to put together a determinant in which, well, the last two rows are the components of the vectors A and B, but the first row, strangely, consists of the unit vectors I, j, k. What does that mean? Well, that certainly is not a determinant in the usual sense. You cannot, if you try to put that into your calculator, it will tell you there's an error, I don't know how to put vectors in there. I want numbers. What it means is it's a symbolic notation that helps you remember what the formula is. So the actual formula is, well, you use this definition, and if you use this definition, you see that it's I hat times some number